Okay, hi everyone. Happy to be here today to introduce one of the webinar talk for GERAD. So today we have the pleasure to host Laurent Pagnier from the University of Arizona. So Laurent is a visiting assistant professor at the University of Arizona, and I'll let him introduce himself to get a bit more background, and then he'll present his talk on physics-informed machine learning for complex systems, a focus on power system application. So thank you very much, Laurent, and the floor or the virtual room is all yours.
Okay, hi everyone, and thank you, Antoine, to invite me for this webinar. It's really nice to be, remotely, but at Montreal, because it's a city that I like a lot. Okay, so who am I? So, this is me. So, you can see that it's actually, giving this this presentation is actually almost a birthday present for me. So that's pretty neat. So I'm Swiss, and I've studied at the EPFL. So my main research interests are, the energy transition, also, how it will impact the power systems, and to understand that I'm using mostly nowadays machine learning, and I'm also as a physicist, I'm also interested in just complex systems, because power systems are just a type of complex systems, and I have plenty more. And I'm also on the process of being promoted a research assistant professor at the UFA. So as you can see, it's also a beautiful campus, so please come and visit at some point. Okay, so now, as a general motivation, so probably this audience doesn't really need a motivation, but it's always good to say that global warming is something that is real. So here, it's, as I'm Swiss, so this is Switzerland, and you can see that. So that's the average temperature over Switzerland for something like 50 years or so. So blue means that it was colder than the average, and red means that it's over the average. And we can tell that the recent years were among the hottest years that we have ever seen. And on the right-hand side, it's the well-known glacier in Switzerland. And so, in Switzerland, we do have maps from really accurate maps since the 19th century. And so you can really tell that this glacier used to be way larger than what it is currently. And then also now a general motivation about the power system. So we know, we take it for granted that if we plug an appliance to a power socket, we will get power. But to make this work, it's a complex machine, and if it fails, then it can fail pretty badly, and it will also cost the life of people. So it's really important that power systems are really robust and reliable. Okay, so now I'm just gonna go through the basics so that we all know. We are all on the same on the same ground. So basically, what I'm gonna use mostly for this talk, at least for the kickoff laws. So we know that the current going into a node will exit. There's no creation of current, and also the voltage over a loop, the voltage difference over a loop is equal to zero. But that's the physicist way to show those equations. Now, if you are a power system engineer, then you probably know that nowadays, the power grids, they're mostly AC, AC power. So we do know that there was this war of currents, and so Tesla AC won, mostly because it was easier to transform the voltage, transform voltage to higher voltage. And so, the power is actually oscillating at 60 hertz here in Northern America, which so it's like this sine wave that we see on the right hand side. And we all know that if we just use like a stroboscopic light and we just flash with the right frequency, then this point that is actually like traveling over this circle will be always at the same spot. And so that's what is called the phasors. And that's the representation that is used to describe the power flow, well, the kickoff flows in this power systems engineer's way. And so here, well, that's the power flow equations that you probably are all familiar with. But so yeah, on the left-hand side, you have the power that is injected, well, either consumed or injected into the grid. The voltage, phases, and magnitude are also part of this equation, and the transmission grid is actually modeled by or described by line susceptances and conductances. But so that's the sort of like the full equation. But usually, oh yeah, and also yeah, you all know that. But the real power is what you can really use for to perform tasks. And the reactive power is more like this sort of potential energy that is used in the system. So that's a clear way to say that, yeah, this is not really something that you can use. It's a bit like the foam on top of your beer. But yeah, so in transmission grid, usually the susceptances are way larger than conductances, which leads to this often used approximation, that is to say, well, the conductances are just equal to 0. So it's this lossless approximation, or also known as DC approximation. Well, if you linearize the sign. And so you get what is in this box, where you also assume that the voltages are close to their nominal rated values. Okay. Now let's just also briefly mention how electricity is traded. So here I will use some assumption that, well, the market is following the law of supply and demand, and that we have enough capacity to sustain the load, and the load is seen as inflexible. And in this framework, well, the easiest way to trade electricity is just to sort all the generation according to their marginal cost. So as it is shown here, and so it's called this merit order curve. And then as the demand is thought as inflexible, well, it gives you a point on this curve, and this point then assigns a price for electricity. And so yeah, and that's why, for instance, when you are at maybe 6 p.m. so basically when the demand peaks, the price also usually peaks. Okay, but then how do you formulate this like in a more mathematical way? Well, a way to sort of, I don't know if it's a surrogate. Well, actually, here in the US, it's the market is roughly a more complex. It's roughly what I'm gonna describe, but in a more complex way. So it's called like economic dispatch, and so the goal is just to minimize the total cost of electricity generation subject to some constraints. So like the minimalistic version is this. So it's just that the total, and the total generation should meet the demand. And this is obviously in the lossless approximation. So yeah, we can really say that it's an equality, which is obviously not exactly true. And then yeah, this cost function, well, there's different ways to describe it. Usually it's thought to be either a linear function or a quadratic function. Sometimes people goes even crazier and use piecewise linear or cubic functions, but usually people stays with something like quadratic functions, cost functions. Okay, but so then we can also so here, well, it's still unconstrained, but you can always use this this approximation that I introduced earlier to also make sure. I don't exactly remember what I want to say with this one, so but it's pointless. Okay, now we can also introduce thermal limits. So we know that, for instance, the different lines. Oh, by the way, so if you have any questions, just please interrupt me at any point. Here, for instance, we just add flow constraints. So we know that a given line can't carry more than a given rated value. And so if we want to make sure that the economic dispatch that we get, so how much power will be generated at each station, will not violate these limits. And so this is also part of this optimization problem. And then obviously you can make this economic dispatch as complex as you want. So you can introduce, for instance, also say that a given generator can't really increase its production from an hour, a time step to the next one, more than some given ramping rate, etc., etc. You can also add some cost for starting up the generator, for stopping it, etc., etc. Okay, now in this talk, I'm also gonna talk about, as I said, I'm interested in machine learning. So it's really machine learning in the purest sense. So it's not that it's just a way to fit different functions. So that's what I mean by machine learning. It's not like people say AI, but I don't think that, those methods are not sentience. They are just it's mostly methods that you have some function that you want to fit, and this is what machine learning is. Okay, so with this caveat said, okay, now I can move to the first first application. So in here, still small. The goal for this part of the talk is, can we learn the parameters, so those line susceptances and conductances, just from measurement from the system. So you have this huge system. So here it's the US, and you have this map, but each of these lines that you see is actually a power line, and each point is a substation. So it's really huge machine. And so we want to have good models as to help people that are in this control room to operate it, because we know that with more renewables that are actually fluctuating sources, it's going to be harder and harder to operate those large systems. And also if you can actually assess estimate those parameters in real time, then we can probably say, it's either this line is actually pretty loaded right now, and it's probably really saggy, because we can tell that its physical properties has changed. And so and hopefully we can also say, actually this element is aging really badly. So it's time to repair or to do something, because we can tell that it's not as it used to be. So there's probably something that has to be done. So yeah, here it was really a close call. You can see that those hooks, they just keep the line attached to the tower, and in this case, well, just by oscillating with the wind, it wore down till, like, yeah, it was almost too late. Okay, so back to the powerful equations. So if you have this set of equations, but then you can also sort of rephrase them into the sort of this ML jargon. So in this case here, you can say, oh yeah, I have input, so I would have voltage, magnitudes, and phases, and then outputs. So let's say the active and reactive power injections. And the goal would say, okay, now I don't know what is my my system. I just have those input and outputs. Can I learn what the system is? So basically, what are the susceptances and the conductances of my my system? Okay. Oh, and then you can also reverse it. So see it as yeah, the voltages being the output, and the injections being the input. Okay, what do I want to say here? Oh yeah, well, and then, well, it's as usual. Well, when you want to apply some machine learning, well, what you have to do is to define a loss function. So in this case, well, it's just some supervised learning. So we have the output, well, so some samples for these outputs, and we just train the method to well, yeah, to reproduce the output. But oh yeah, what I should mention is, yeah, so it's not a black box. Well, if we know that our samples are actually following the powerful equations, we can just say, yeah, I know that this is, I don't want to use like a neural network that is a fully connected neural network and just try to mimic what's going on. I know that it's these set of equations that should be satisfied. I just don't know what are the G, IJ, and the BIJ. And so this is what you encode, and you just try to learn those parameters. And once you've trained your this method, then the parameters that you've learned are actually, well, they have some physical meaning. So then you can compare them to the actual susceptances and reactances in your system. And so that's what I do here on the right-hand side. So the initial values for, well, so as I didn't know anything about the system, I initialized all the susceptances and reactances to a given value that is shown here in green. And then after what was learned is in red, and the reference is in blue. And yeah, you can tell that it's not exactly, you don't get exactly the same value. There's some discrepancies, but yet what you learn is pretty close to the real values. And yeah, okay. And then, yeah, here we also studied how many samples you need to get a good reconstruction of this admittance matrix. And actually, like, if they are different enough, you don't need that much. Like, even with 100 samples, you already get or even, yeah, 20 samples, you already get a good reconstruction. Now, oh yeah, for up to now, I was assuming that I knew the structure of the grid, but just missing the values for the BIJ and GIJ. Now, assume that you don't know anything about the system. So you are in this configuration A That is just you have an all-to-all coupling with this initial value. Can you still learn the sort of the right structure for your grade? And the answer is yes. So basically what we decided to do here is to say, oh, you have, if a connection goes below a certain threshold, it means that there's probably no connection between those two points. And so we just kept removing connections until we get something that was, until we get what is in B. And B and C is the reference. So the thicker the line is, the stronger the connection is. And obviously you can tell that it's not exactly the right system. There are some spurious lines, etc. But yet you get a good idea of what the structure of the system is. Okay, now if I go to partial observability, well, maybe I will go quickly over this because I see that it's already almost 9:30. Yeah, this is just now, well, for the time being, I was assuming that I had information over, well, for each bus in the system, but obviously it's not true. So you have only measurements devices at a subset of the substations, as you can see here. But in this case, if you have just partial observability, what you will get is a reduced model, an effective model. Yeah, the training is a bit more complex. You need to also use some regularization and add a second, well, neural network in this case. And what you will learn is sort of what is known in the PS community as this Cron reduction. But yet you can still reconstruct this pretty accurately. So this was done on a way larger system and with almost 4,000 bus system. Yeah. Okay, now, do I want to say anything else on this one? No, let's move. Okay, maybe let's move on to the next the next topic. So this topic is about sort of making the solving. So this is, the energy market is mostly about solving this type of optimization schemes. And well, this may seem pretty easy, but if it's for a really large system and you need also to account for variability due to due to like new renewables and stuff, well, you need to run a lot of those. And so if you can make this computation faster, it's really nice and important. So this is just a reminder of the scheme that we want to solve. And so this can actually be rewritten as a Lagrangian. Here I will leave a few things under the hood. For instance, we use this, so phi is actually the PTDF matrix. So it's a way to sort of get rid of the angle, the phase angle theta. But I don't really want to go into all the details. But so what you need to understand is that, well, basically this optimization problem can be rewritten, well, it can be solved just by solving a system of linear equations if you know which line is our binding. What I mean by that is which one of the lines are at their maximal value. And if so, you get a subset of those mu k up or down, that you only have like a subset of well, for those lines, the mu k with a bar on top or on the that are non-zero, and that's what I call here with a what is described with a star. And so it's just about solving this set of this system of linear equations. But to do that, well, you need an oracle to say, okay, you know what, it's going to be line number 25 and 27 that are going to be at their thermal limit for this sample. And obviously, we don't have access to a real oracle, but we can train an agent, so a neural network to give you this information. So it's just giving you a Boolean. So for each line, so is it at the maximal value or not? And so, yeah, in this case, for instance, it would be the agent would say, yeah, okay, the line between bus 13 and 14 is actually at its maximal capacity, and also the one between line bus 2 and 3. And once you've got this, yeah, how do you train your agent? Well, it's always the same jazz, actually. So you have to define a loss function. And here, yeah, so it's just about making it predicting correctly whether a line is binding or not. And we've done that. Okay, this plot is actually way too small, but what you need to understand here is, so we have 3 different configurations. So obviously you can have configurations that are trickier than others. And then for each of those configurations, we have like 500 samples. And what we plot here is the max error. And well, it's almost 0 for most of them in configuration 1, apart from maybe 1 or 2. The second one is a bit trickier, so we fail for maybe 20% of them. And then in the third case, well, it depends on the volatility you have, but it can be really bad. And so the goal, so it's sort of, the preliminary results are that it works pretty well, but there are some tricky situations where maybe we should have, yeah, the agent is not really able to find the right answer. And then, well, when you compare this to what was really obtained by solving the OPF, it's not that great. But we have different leads to make this actually yeah, more robust. And so it's work in progress. And also the problem that we were solving here is a bit too simple. So we are working on extending this to adding for instance, a curtailment for the wind farms, load shedding, and different stuff that is also part of the, well, real electricity markets. Okay, so that's sort of what I wanted to say on this topic. Now I will move to something, oh yeah, a bit new. So up to now, everything was sort of in this framework, sort of, as I mentioned, like this stroboscopic light, where you are in this sort of steady state. Well, it's a snapshot, and you assume that everything is sort of fixed. But in reality, porous systems are never really in an equilibrium state. You have always some mismatch between the generation and demand. And if so, well, the frequency of the grid will evolve. And so following this swing equation that you can see here, that is, so if you have more demand than generation, well, the frequency of the grid will decrease. And obviously, this equation can't be sort of exact, because in this case, if you had any imbalance, well, the frequency of the grid will either go to infinity or to minus, so it will diverge. So obviously you have some control, and here, well, if you add, for instance, primary control, then here is what you get. And in this scheme here, well, you can see the influence of inertia, of the system inertia and primary control. So the inertia has the main impact of inertia is on the rock-off, so the rate at which the frequency change at the beginning, and also on the nadir, and the primary control has some effect on the nadir and also the post-fall frequency. Okay. Now, well, we all know that, so renewables are not equivalent to like a conventional unit. And it's the case on different aspects. So, well, it can be how you trade, well, how they enter into these electricity market schemes, because, well, for instance, renewables, that they have almost negligible marginal costs. So but they are also non-flexible, non-dispatchable, etc., etc. But so here, the main difference that we're gonna focus on for this part is the fact that, well, they are inertialess. So you can tell that there's nothing, well, for a conventional unit, well, it's a big sort of motor, so it's a big spinning wheel, and well, with a PV panel, you have no inertia. Okay, and so here, just to tell you, so here, well, it sketches a situation where you have a lot of conventional sources connected to the grid. And then if you remove some, well, yeah, you're gonna have a larger rock-off, and also the nadir is going down, and etc., etc. And obviously, some people in the audience might be familiar with the fact that, yeah, if you have renewables and some power electronics, then you can make, you can actually sort of mimic the behavior of a conventional unit. But the question is, well, do we really want to do this? Because that might be something similar to what I'm showing here. Yeah, and then also just mention, so that's beyond the scope of the current, well, the present talk, but most of our appliances, well, they can handle varying frequency. So the fact that the frequency should be really close to a certain known nominal value might be something from the past, but yeah, once again, that's beyond the scope of this talk. And so we're gonna assume that yes, it's the case. We still want to be able to maintain the grid close to some given nominal frequency. Okay, so here I go for like a bit more detailed model of a power system, and so here the different buses. So if it's a generator, you will have inertia, and so you will have this ODE. But if it's a load, you have only a damping term, and so this is sort of the transient dynamic model that you have for a power system. And yeah, obviously, that's just a crude approximation of what is the real response of the system to a fault. For instance, here you can see that there is a fault somewhere in Switzerland. Then you have this primary control, so what I model in this swing equations. But then obviously in reality you have secondary control that kicks in after a few seconds or minutes, and then also you have this tertiary control that also is there to make sure, well, to account, well, to replace this missing power station. And yeah, the sort of the validity of the swing equation is roughly like 20 to 30 seconds after the fault. Okay, now what I want to do here is to just sort of motivate why we are trying to use continuous model for power systems. And so it's a bit as what I showed previously, where I had this all-to-all coupling, because if you have no information about the grid, well, you start from assuming that everything is just connected, and then you sort of try to use machine learning or some technique to learn a bit more about it. And so here we just say, okay, assume that you have a large porous system, like here it's the Eastern interconnection here in the US, and you can see that there's a fault in Florida, and it propagates, the fault, you can see that propagates through this grid as well, a bit like the ripples that you see on this pond. And so it was like sort of like seeing that just sort of give us the impression that you can actually model those porous systems as a medium. So, because if you look at them from far away, it's sort of like a mesh, yeah, so maybe we can just treat them as a medium. And if you're not convinced by this analogy, well, you can also just say, yeah, it's a way to, if you don't know much about your system, you just start by, yeah, placing a mesh and then sort of tuning the different parameters so that you can get a reduced dynamical model for your system. Okay, so back to the swing equations now. Okay, sort of symbolically, to go from the swing equations to this continuous model, you just assign, well, values that were at a given position. Now you say, well, I want to spread them over two dimensions. Well, and so the main step might just be to embed first the values that you have into 2D, and then distribute them by some mean. Okay, and then yeah, the equivalent to this swing equation would be something like this PD model that I show here, and the goal would now be to find a way to get good values for the inertia damping, etc. Okay. So now assume that for the timing, we assume that we have access to ground truth. So it would be just a discrete model of Europe in this case. And yeah, we really have access to for the timing, all the information about the system. And so then, yeah, what we do is just what I just mentioned. So you embed the values that you have that are at given locations, and then, well, sort of, you want to smooth them to distribute them over the whole system. And so we've tried that just as a proof of concept, and then we just did some like simulation with this model, and we compared it with what we get from the ground truth. And so here is the frequency, the evolution of the frequency at 4 different points in Europe. I forgot to place them in the map, but yeah, I think the fault was somewhere in Greece, and then you have A is somewhere in the Balkan, B is probably in Switzerland, C somewhere in Italy, and D in Spain. And the blue curve is what you get. No, sorry, the solid curve is what you get from the real model, well, the ground truth, and the dashed line is the dashed lines are what you get from our reduced model. It's not perfect, but you can see it as a proof of concept. It works. And then another point was also, can we actually reduce the model? So here we just decided to go for a Fourier filtering and reduce the number of parameters by a factor of 3. And yeah, we get sort of exactly the same results as what we had with the full model. So that was a good sign. So you can get a PDE model that is able to reproduce the ground truth, so to a certain extent, with really just a few parameters. But okay, but so that was just knowing exactly what the model is. But now what happens if you just have access to some time series about like for a few historical faults in your system? So here, for instance, yeah, you have a fault in the system and you have time series. Can you learn, for instance, what was the distribution of inertia at that time over your system? And once again, it's always about creating a loss function. So in this case, we went for this loss function. So it's basically, you have different points of measurement. So let's say you have different ones, and for them you have a reference time series, no, different, yeah. And then you want your model to reproduce what you observed at those locations. Okay, now then you want to compute the gradient of this loss function. If you do this straightforwardly using just automatic differentiation, well, you will see that it's an ineffective and it's memory intensive, etc. And my take on that is, well, if you're a bit familiar with these neural ODEs and stuff, you can sort of tell that solving this PDE is equivalent to, well, symbolically as a really deep network. So it's not an efficient way to go just this way, but then you have also this adjoint sensitivity method that is just a way to sort of compute the gradient of a loss function that would be an integral, as you can see here. And once again, it's just about writing it as a Lagrangian, and then you have this adjoint problem. So basically what you need to get the gradient, you need to integrate the first forward in time and then backward in time for these adjoints, and then you have your gradient just by those, well, integrating twice the dynamic of the system. Okay, now here, yeah, as I mentioned, that we want to sort of use as little parameters as we can, and so here we decided to use the eigenmodes of the system. Here I show a few of them, and yeah, so we would just use some modes to parameterize the inertia and the damping distributions. Why we decided to do that? It's just because they have, well, that now each parameter would have a non-local effect, so that's pretty neat. Yeah, and also, yeah, we want to guarantee that the values that we get are physical, in the sense that, well, inertia and damping should be positive. So we have to do this sort of constraint gradient descent. And do I want to go into more details? Probably not. And so here is the full experimental setting. So we have measurements at all the orange dots, and we have time series for all the stars here. Why the stars are not more distributed than this is because I decided to make a 900 megawatt faults, and I decided to make this only at generators that are larger than this value. Okay. Now, yeah, here is some preliminary results. So on the left-hand side is so this ground truth, so this discrete model. So each you have inertia and damping, and obviously if the disk is larger, then it means that you have more inertia. And on the right-hand side, you have what the model is learning over the epochs. Well, it seems that it is actually able to distribute it mostly on the right spots. So that is pretty neat, and well, but it's still working in progress. Okay. Oh, and yeah, maybe why do we need those new methods? Well, it's because most of the inertia, well, no one really knows exactly where inertia and damping is, mostly because up to a quarter of it is sort of just comes from distributed sources that the operator of the grid can't really see, and yeah, don't really know what they are. So it would be nice if we can have methods that are able to to assess what is the exact map distribution of inertia and damping. Let's move on. I'm gonna probably skip this because I'm running low. I'm running probably late. Just mentioning that we are actually, well, obviously creating some different frameworks for those tasks. Let's move through this, and also Pentagram, so which is the model that I used for those simulations. Another point that I might also just briefly mention this. By the way, Antoine, you can actually do we want to have a few minutes for questions?
Yeah, I think that would be great if there's a question from the audience.
Okay, so should I stop in like 5 minutes or so?
Sounds good.
Okay. So let me just go quickly through this. So now it's also nice, as I mentioned, so I'm also interested in complex systems. And so here, for instance, you have another, this is just like, for instance, up to now, I was focusing mostly on power systems, but obviously you have different other systems that are also connected to it. So it can be like an information, like communication system, but here it would be like a gas system. So for instance, in Israel, most of the power plants are powered by gas, and so there's a strong interconnections. Well, yeah, they are interdependent, those two systems, but they have different time scales in the sense that, well, in the power system, the transients are pretty short, fast. And in the gas system, well, a transient can last for minutes, if not hours. So it would be nice to see, if you can, like this, if you by doing something in the power system, you can sort of trigger a dangerous situation in the gas system, or vice versa. And so I'm starting with modeling this kind of networks and their sort of synergy, how they work together. That's a work that I'm currently doing with NOGA, which is the TSO, well, the operator of the grid in Israel. Oh yeah, and I was in Korea last year, and so the situation is in Korea is roughly the same. They also rely strongly on gas, and so they have those two systems. So it's actually a pretty common way. It's actually what my findings on the Israeli grid might also help Korea. Okay. Now I'm also doing some outreach activities. We are publishing some technical reports to help making decision. Here was, for instance, about building a large solar farm somewhere in the Swiss Alps. The politicians, they didn't really know what to think about it. So we decided to do this, to make this report. And finally, just going quickly through, I said, I'm now trying to find ways to apply what I've learned about machine learning and physics informed machine learning to, well, for instance, physics in this case. And so physics here, it's particle physics. So I won't go into all the details, but you have a set of equations, and so you want to tune some electromagnets, so those big magnets here, to achieve some tasks. And the goal would be to use some machine learning to make this to tune these big accelerators in a more efficient way, because for the time being I think it's still someone having knowledge and a screwdriver going to tune all those by sort of hand. I think I'm just in time so I'm probably just gonna stop and skip that. So I'm ready for any question now.